So as we wrap up how the stream's function may affect the stream's form, we need to realize then that balance is always trying to be achieved. So the stream form or the stream morphology will change if equilibrium isn't occurring. So it's important. We tend to think of the banks eroding on a stream as being an unnatural bad thing. We think of these floods where the water leaves the banks and drops all this sediment as being an unnatural bad thing. And although they can cause damage, and we can, depending on our values, associate that with something negative, we have to remember that rivers change is natural. They are not static. They do not stay the same. Their form will not stay the same, and their function will not stay the same. However, humans have induced change, and that change can speed up the process that the river changes in its form or function. And it can change the capacity of the stream, how much sediment that stream can hold. So how do we change our rivers? Well, one of the most obvious is that we can create dams and we can divert water. Obviously, when we create dams, we're going to change the amount of water heading down that stream at a time. And we know that the amount of water determines how much sediment it can carry, determines how that river is functioning, which will then affect how the form of that river continues, how it changes at that point. So we change the flow regime with our dam and diversion. We channelize. We do this all the time in cities. Channelizing is when we say we don't want there to be twists and bends. We want the river straight, because the wider the river is, the less land there is available for our terrestrial needs. And so we do that through armoring the banks so that that erosion that's occurring on the outside of a bend can't occur. And when we armor it, we could do it with just straight concrete. We do that a lot. We can also put down what's called riprap, which is large rocks where that water wants to start eroding on the side of the bank. We'll just put in large rocks, and they absorb that energy to some capacity instead of letting the river take more sediment to try and reach equilibrium. Okay, so that's a little bit about the form and the function and why that's so important, because it just tells us what the river's doing and what shape the river is likely to have. Well, that shape then affects the physical habitat that's available for aquatic organisms. And the physical habitat is highly dependent upon the river's gradient, how twisty-turny or the sinuosity of the river, the velocity or speed, the substrate, that's what's on the bottom of the river or the bed load, and the cover, the vegetation that is occurring within the river. All right, another few diagrams here for some habitat terminology. So we have riffles or rapids when the water is flowing over rocks. And a lot of times those lead into pools or eddies, and these pools oftentimes are on the outside of a bend. Remember, water is probably picking up more sediment in those places, and then it picks up speed as it heads around the bend. And as it picks up those speeds, we call those a run or a glide. And then it may hit another riffle because some of that sediment has fallen out past that run, and so the water then can gurgle over the top of it. Some pictures of that. Here's the riffles, just barely hitting over the rocks. When it's larger rocks, we might call it a rapid. The runs and glides are the areas that connect those pools and riffles, but the water is moving fairly uniformly across the width of the channel in those runs and glides, and generally there isn't much of a curve associated with it. And then the pools that often occur on the outside of those bends and can have fairly deep holes in the bottoms of them. That's a nice refuge for fish to try and get out of the current, as most fly fishermen know. So switching gears, we've been talking about the lotic habitat. It's time to switch over to lentic habitats, or our lakes and our ponds, more of our still water systems. So the lentic habitat has some spatial stratification going on. So let's look at that. And on Friday, next Friday, we're going to do some surveying of this zone right here called the littoral zone. That is the area that is around the edge of the lake that has some rooted vegetation. It's typically shallow, and we have vegetation within that zone that's rooted, and that might be aquatic vegetation, might be terrestrial vegetation, but that transition there is called the littoral zone. Then the limnetic zone is the rest of the pond, the lake, the body of water, as long as sunlight is able to penetrate through that water. Underneath that limnetic zone, which is not in my diagram here, that's called the profundal zone, and that is usually only in deep water bodies where the sun cannot penetrate that deep, so there's no photosynthetic activity going on that deep. Therefore, your oxygen levels would be lower down there. And the very bottom of any lentic habitat is called the benthic zone. It's just the bottom. We also have some thermal stratification going on. So not only changes across the landscape, but going down deep within the landscape. So we have a few terms here to know too. The warm water on top is called the epilimnin, and the cold water on the bottom is called the hypolimnin. And then the area in between is called the thermocline. And sometimes the epilimnin is actually very, very shallow, and the hypolimnin is very, very deep. It doesn't appear so in this picture, but there are, it just depends on the climate of where the lake is occurring. I imagine if you've ever swam in a lake, you've realized that your toes are much chillier than your shoulders if you're treading water. And that's because of the thermal stratification going on within that body of water. Again, remember that it's sunlight that's going to add most of the temperature increases to the water. So when you have this stratification going on, you also will have differences in aquatic communities. You'll have your cold water fish down here and your warm water fish up here, and they're in different niches within that aquatic lentic habitat. What are some of our threats when it comes to managing aquatic habitats? Well, not so different than threats for terrestrial habitats. Some, though, are unique. Well, water chemistry, that'd be something that is unique to aquatic systems, obviously. And we're not going to get into each of these chemical components of a water system, but do know that the amount of water the amount of oxygen that can be dissolved in water is dependent upon two things. It's dependent upon the temperature, and it's dependent upon the elevation. And it's an inverse relationship with both. So as you go up in elevation, the water can hold less oxygen. As you go up in temperature, the water can hold less oxygen. So therefore, your warm water species do not need as much oxygen dissolved in the water as your cold and cool water species. Turbidity has to do with the sediment and the cloudiness of the water. Temperature is obvious. Salinity has to do with your negative ions in the water, and it's highly correlated to salts, obviously, that's the name, but it also has to do with how much electricity can be conducted in the water. And then hardness is your cations in the water, and that contributes to exoskeletons with crayfish and aquatic invertebrates. So we have changes in this water chemistry can affect all the aquatic life in the system, and your book does a nice job of going through some of these things, so make sure you've read that. Invasive species, just like on land, invasive species can wreak havoc to aquatic systems too. Changes in the habitat, that's changes to the form, changes to the riparian habitat, and changes to the river channel itself or the lake itself. And then here's a whole bunch. We could overfish it. We could have winter kills. Your book explains what winter kills are, have to do with dissolved oxygen and temperature. We could have algae blooms from eutrophication, which we've already talked about in this class, and your book covers that pretty well too. If we have too many fish in a system, they will not grow to their maximum length, and so we'll have a stunted fish population, a stunted small group of fish. We could have draining going on to either a river or a lake system that would affect the aquatic life in there. Unnatural scouring, where the river is digging down in because it has no place to grab other sediment and equalize that balance. Water depletion at the end of this a series of videos. There'll be a cool little video on maybe how we can tackle that problem in our society. And we could probably come up with a lot more threats. There's a lot of things that can affect our aquatic systems. Okay, so we're going to look at fisheries versus wildlife management. Sorry that that's cut off a little bit there. The wildlife system does differ from a fishery system in a few ways. For one, all the animals grow to a potential size, and that's as big as they get. But in a fishery system, it's indeterminate growth that's dependent a lot upon the habitat and the competition occurring in that system. So like I said, if you have too many fish in your system, then you're going to get small fish, and they won't be able to just continue growing throughout their life. On a wildlife system, the population is a count or an estimate of individuals. When we do it on a fisheries system, we're looking at biomass, so we're usually talking about the number of pounds of fish rather than the number of individuals of fish. With wildlife, we harvest. The harvest is managed to support natural reproduction and recruitment. In a fisheries, we often allow harvest that goes beyond what natural reproduction could occur because we supplementally stock so much of our fisheries. And with wildlife, we have no limited artificial propagation. Either we don't have it or it's limited. We don't grow wild animals in captivity too often and supplement wild populations. Obviously, you can think of the black-footed ferret being an exception to that in some endangered species. But in fisheries, we do it all the time. We artificially propagate animals, put them out into the aquatic systems, and then enjoy fishing for them. So the goal of a fisheries management system is to maintain an optimum and sustained yield of desirable fishes. Well, obviously, what's desirable? And the thing about fisheries is desirable might not be native. So it goes back to our value system here. But most of the fish that we fish for in Colorado are non-native species to Colorado. So how do we achieve this goal? Well, we need to maintain habitat. We need to improve habitat if it's lacking, like we do with other habitat goals. We need to control invasives. We need to have some kind of balance between predators and prey in a system. And we need to stock. And like I said, most of Colorado's sport fish are stocked. This video is going to be linked under your assignment. I'd like you to watch it. It's a very nice overview of the hatchery systems here in Colorado. We need to be able to monitor and sample our fish population. And that is really important and really fun. That's a part of fisheries management that I think is a lot of fun for a lot of people. So we're going to take a look at the methods that we use to do that here real quick. So population monitoring can be passive, and one method of using passive sampling is gill nets. So with gill nets, you put this line in the river or in the pond. Usually this is used in standing waters. And there's a series of different size holes in here, and as the fish swim through, if they are not small enough to fit through the hole, then they get caught, and if they try and back up, the net catches them on their gills. So they get stuck there until the biologists come by and pull them out of the net. Another passive method is called a trap net. It's a little less invasive than gill netting, but essentially the fish swims up to this line. You can't see it super well, but this line goes up the bank out of the water, and so in that literal zone, and the fish swimming along the shoreline hits this wall. If it goes up, it goes out of water, so it goes down and it swims through a series of hoops until it's caught here in the end. Now this is pretty non-invasive. It doesn't really hurt the fish. The only thing that can really happen to the fish that wouldn't be healthy is a bigger fish comes in and eats it. So that's one limitation with this sampling technique. But you leave this in overnight and see how many fish you collect. A passive sampling, an active sampling method would be seine netting, where you take your net and you drag it along the bottom as fast as you can and up and out of water and see who you catch. This is a really large seine net. You can seine net all the way across the river system or use a really small one like this. And then electrofishing. This is a blast where you mix electricity and water. It stuns the fish float to the surface. You scoop them up your net, you put it in your bucket. They start swimming around again. You count your fish, you weigh your fish, you measure your fish, and dump them back in your water. And then midwater trawls require a boat. This is used in more large lakes and open water systems. And you just drag this net behind. It's used for larval fishery because it's a good way to catch a whole lot of little critters at once. And finally, creel surveys. Creel surveys are important ways of gathering information, just going around and asking what everybody caught. So to wrap up,